You get, did you get? Very nice. Okay.
Only this
Four blackboards,
yeah.
huh? Okay, okay. It doesn't matter. Yes, I think so. It's, in any case, it's better to. Uh, so, shall we begin? Oh, yes, already. Okay, so last. I shall. Okay. Hmm? Oh, okay, okay. Yes, last time we uh, so discussed the we obtained, we established a global monodromy representation of Gauss hypergeometric function as representation homomorphism from fundamental group of P1 minus 3 points to GL2C. That was our main result of last. Where is it? Okay, okay. And how can I put? I use only these four. Right? Do you know how? Like this. Okay, okay. Okay, okay. So, yeah, and I recall you. So, shortly, I recall the result, main result. So, 0, 1, this is, yeah, FPQ itself, somehow, constant times, up to constant, it's F, so F01, F01 is constant times, non-zero constant times Gauss hypergeometric function. That can be calculated somehow in gamma factors and so on. Yeah. And so we restrict ourselves on our attention on. In fact, the point is that we have, even though we have 6 cycles, 4 to 6, 6. So PQ, if PQ runs among these this set, then we have 6 different types of integrals. But there is a relation. So we found a relation between these 4 relations. There exists 4 linear relations between these 6 integrals. So in fact, over C, it is enough to consider 2 integrals. 6 minus 4 gives rise to 2, so 2-dimensional subspace. And as a basis, we have chosen F01 and F1, 1 over Z. So I denoted by F1, F2, somehow. So this means that we have branching points of this integrand function. And consider these integrals not cycle integral, rather. So this one is some f01. So it's a chain integral. It's a chain integral that can be transformed into a cycle integral in making use of Pohama cycle. And this one is so one was that. That it denotes. So for the simplicity, for the sake of simplicity, is one f1 and f2 unobtained. So this is a quite important procedure to see really the den twist of cycles. This is a chain, but in any case, essentially it is the work was done for cycles. And the result was like this. So C1, C2, where is it? F1, F2. So F1, and so this is fiber. Okay, fiber. And Z, it depends on Z. And if Z coincides, so this is base space, this space, minus 0, 1, infinity, 3 points, points where these functions become singular. So Z, where is it? 1 over Z. 1 over Z equals 0. That is, say, infinity. 1 over Z equals infinity. That is 0. And 1 over Z equals 1. I have three singular points. Say 3 points, singular points for these functions. So branching point of these functions in Z, of course, it is a parameter function dependent on a parameter. And so our task was to get monodromy representation L1, L infinity, so we have 3 loops, but as you see that my notation, what was it? The ordering of the maybe somehow L0. Yeah, in any case, so L0, whether which in case this L1, L infinity, not to confuse with. In fact, the ordering of these loops is can be confusing. Yeah, but so in any case, so these 3 loops, if you turn around all of them, they need to give you identity trivial element, and the pi1 p1 minus 3 points with fixed point. So we have so we associate to each branching point of this Z function on the space P1 minus Z, 3 matrices, pi1 to GL to C. That is, say, what happens, some L, some loop, of course, and that's if you consider analytic continuation of these integrals along some closed loop, closed curve, then it gives rise to invertible matrix in GL to C, rho L, rho OL, that acts on the space of these integrals. These integrals. And so we denote it matrix. So say rho, maybe it's better to write somewhere here, rho Lj, I don't know by Hj, j equals 0, 1, and 1 over z. There's three possibilities. But because of this relation, it is enough to consider only these. Sorry, infinity. No, sorry. 0, 1, and infinity. There I have three. So matrices, but because of this relation, H infinity, if I pass the contravariant expression, then it will be identity in GL to C. So this Hj is, it corresponds to, so rho infinity, that this is the monodromy action on these integrals. If one considers analytic continuation of z from certain fixed point along a loop, turning around infinity once, only once, around infinity, yes. So, okay, and this is, so we obtain a concrete expression of these. In fact, it is generated by two monodromy group. Is generated by two matrices, 0, 1 or 0, infinity. You can choose two of them, because the third one you can express with 8 of others. This is the point. This reflects the fact that our fundamental group is generated by two generators. That's this. It reflects the topology of these regular, say, set of regular values of these integrals. So monodromy generated by two matrices, it is enough to calculate only two matrices, H0 and H1 or H0 infinity, to understand the whole monodromy, so that to be able to write down explicitly this rho L for any L. It is enough. So that last time we calculated H0 and H1. So H0 was with respect to this basis, H0. So H0, say, yeah, I always so L0. We calculated. We established this fact: F1 F2 equals 1 e to the power minus beta minus 1 0 e minus gamma, where e I always use this notation, e to the 2 pi I lambda. So times f1, f2. You find f2 is subject to this transformation. So after our notation, or otherwise, there is another way to write it down as so which one is H0? So this one I denoted by H0 transpose of H0, because H0 H0 I use rather, yes, maybe because of this in fact, monodromy representation there are two ways to express monodromy representation. One way is to express by means of matrix that is acting on these integrals itself, but the other way is to act what is acting on the space of how these say C1, C2 as elements from C2 and as action on these coefficients, you can understand. And this is what is written H0 H0 C1, C2. If you write down anew this expression, and in terms of C1, C2, then the monodromy will be the transpose of this matrix, that is, say, 1, 0. So this is somehow maybe L0. This is the way how I denote. I use this notation Hj. And so L1 around this loop, I got this, or we got this expression, this matrix that is equal to that is like this: E1 minus E minus alpha, E to the power 2 pi I, gamma minus beta minus alpha. Oh, no, here. Eta, E gamma minus beta minus alpha, and 0. So we got two matrices. This is H1, and we got entire description of the image of this row homomorphism row from fundamental group to C. That is so row of whether in any case monodromy group it is generated by two matrices, H0 and H1. No, up to some conjugate base change choice of basis and so on. It depends on, of course. But yeah, essentially this. Okay, so today, so this was a lecture of main. What shall I do? Yeah, okay. Maybe I can. So today, I propose you to study not to get this global monodromy group, not in terms of H0 but rather H0 H infinity. So this is not rather the method or the topology, the analysis in topology that lies behind all these procedures that I will explain. It's quite important. It allows us generalization of higher dimensional case of different kind of algebraic varieties, periods of algebraic varieties. This is the subject of this course in general. So so to the yeah, H0 and H infinity, starting from H0 and infinity, H1 I will get from these two matrices. That can be obtained by means of analytic continuation of so-called Mellin-Barnes integral. Integral representation. Mellin-Barnes integral representation. So what is this? So for always we start from some an argument. I need to somehow restrict my argument. A kind of slit, isn't it? Is it right? Minus that is a kind of slit. And that, and satisfies can be. So this one is really this Gauss okay. This is somehow a function defined by series, but we obtained different kind of interpretations in terms of the F01, yeah, the 01 integral, huh? So on. So as a cycle integral, and also C some integration path of an integrand function that depends on 4 gamma factors power s ds. So what is this integration path that I need to first of all, we this integrand function has poles at s for positive non-negative integers, isn't it? Gamma 0, gamma so if s equals so poles are located here. So 1, 2, 3, and so on. This is the pole coming from here. And the poles that arise from here is minus alpha, minus 1, etc. So for the sake of simplicity, to be visible, that I draw on different level, but in reality, these are rational numbers that appeared in y to the power m. So these are so positive rational numbers, but minus beta minus 1, etc. Minus beta minus 2. So these are, and this one does not produce. Denominator can tends to infinity, so that this may vanish. Gamma s equals minus gamma minus some integer, then it may vanish. It can go infinity. It may vanish, but if this factor does not produce pole, and we are interested in somehow residues. To understand this this series as a summation of collection of residues of this integrand function. Okay? So it will be reasonable. So alpha beta was positive numbers. Oh, in any case, real part positive. That was an assumption, or in any case, so these are really zero. Sorry, zero, of course, zero. I have it. Yes, this has pole at 0. So first order, 0. First order pole. Yeah. And as C, this integration path shall be chosen in such a way that to avoid maybe somewhere here. Yeah, simplest way is to choose C minus I infinity, C plus I infinity. This kind of integration path. Okay. So if I do what is this? Yeah, this is entire say statement. Even though it is a one stroke formula, but it contains to show that this is the validity of this equality. We need to be a bit careful about the convergence, for example. This integration is generalized integral. That is, the integration path runs from minus imaginary part minus infinity to positive and infinity. But nonetheless, it does not cause the problem of convergence, thanks to starting formula. I will explain it a bit very shortly. Yeah. So this is and because of this, so okay, at the beginning, to get a feeling how this really works. Suppose that this integral is convergent, we accept if we accept the convergence of this generalized integral. So first of all, the convergence, and secondly, the homologous equivalence of the integration path to the path that turns around 0, 1 to etc. These integer points. That is say, this integration is transformed in how is it? This way. So no this way. Yes, this is somehow negative direction. Okay. I deformed this integration path to a path that encircling all poles. In fact, this function has no poles from except these 3 series, infinite series. So it is very natural to deform the integration path by means of Cauchy theorem. Yeah, somehow, if you accept then, so this will turn into this. That is say, it is minus residue. What is this? It is minus residue of z equals, say, m of this integrand function. Whether shall I denote? I denote somewhere. Yes. So let me denote this this function gs. Gs without 1 over 2 pi. These over including this including this constant factor till here. A meromorphic function so that I denote by gs. Okay. So for the moment, you can fix z. Simply consider as a function, meromorphic function in S with poles, with first order poles along this set, this series. Okay, so GS. Let us gather these residue, but residue of this integration the negative direction. Well, so I must count minus of residue. Yeah. S equals m. S equals m. GS in the case. I prefer to write ds and with respect to which variable. Yeah. So 1 over 2 pi I so has been counted. And so that's it. Yes, that's it. That's it. And summation of m equals 0 to infinity. Okay? So after the formation of this, so it's a residue. Now we calculate the residue, okay, of GS. GS, residue of GS at these points is completely this. Huh? So residue of S equals m E gamma minus S equals minus 1 to the power m plus 1 m factorial. Where did I think that the one thing is that you need to be yeah, you make you change your variables and the gamma t minus t residue. I think that the minus will come from here. Minus 1 to the. I would have just checked. Where is it? Yeah, in any case, if I make mistake, then I can correct. I think that this is right. Yeah. So, in making use of this this formula, this residue is very easily calculated. That is, say, this factor times, everywhere I put simply S equals m. Summation. Gamma plus m and m factorial, gamma m, okay. And this last one is m factorial minus 1 to the power m plus 1, and it is here I have minus, because this minus, and minus z to the power of m, that's it. Yeah, that's it, yes, that's it. So now you see that these minus 1 to the power m cancels. That is, say, I get the following expression, that is this. So I recall that gamma alpha plus m, this Pohama symbol, you see that this is really minus cancels. Minus 1 to the power m cancels, and gamma, yes. So that is, say, alpha m, beta m gamma m Yokohama m factorial z to the power m summation. That's it. Yes. So this equality has been proved for the case of for f. Yeah. Inside of somehow a bit careful about this argument and so on. Yeah. But yeah. So up to this part, we've shown that this equality. So now I pass to the justification of this convergence property. I don't go into the detail, but simply maybe I leave it as a kind of exercise to fill the details. Maybe I could leave it. So I have four. So the justification, this convergence problem, of this integral this. GS. So let me write down as rather it is I turn it into a real integral g c plus I t dt, isn't it? ds I t maybe, but t, so minus infinity to infinity. Now the convergence of equation, so it doesn't matter. So the convergence of this complex valued real integral. Complex valued real integral. Yeah? Complex valued real integral. That's the question. So the point is that I use this fact. So by starting formula, I hope that everybody knows, of course. It was required to prove it to be accepted to enter master course in University of Tokyo as a e to the power minus s. So that is say some lower part, the log gamma s is somehow equals s minus 1 over 2 log s minus s plus O1, yeah, as s infinity, and argument of s pi minus delta. Yeah, somewhere. So s is supposed to be on a this kind of a pi minus, yes, this part. Yes, that's very small thin slit outside of very thin. No, every delta, yeah. In fact, not for some delta, yes, for some positive delta. In fact, that does not matter which. But we want, okay. So like this, and making use of this. So our aim is to see that G, this C plus IT, C plus IT exponential decreases as t infinity. It can be plus minus both direction. So to do this, it's simply it's enough to consider this logarithm of GS function GC plus IT. Say logarithm G C plus IT. That is nothing but logarithm of gamma alpha. Okay, C plus I. Let us know simply S. Simply S alpha plus S. What happens? Alpha plus S plus beta plus S, and then ZS like this. It's true. Log Z. Wait a minute. I'm correct. So because yes, log minus Z. Yes, minus Z. Log minus Z. I minus T. And so plus minus gamma S minus S gamma minus gamma S plus gamma plus S. Okay. In fact, the point is that so how it's depends on S. So S log S. S log S. So in making use of this, I skip the detail somehow. The calculation is that is quite easy. So in making use of this, G. So this G. Or even, in fact, it is not so. Yeah, C. I can move C if I have with integration path. I can move somehow like this to put C equals 0. As T is large enough. Huh? So the estimate, to the estimate, I can so consider this kind of function, the asymptotic behavior with this. That is O to the somehow T alpha plus beta plus minus gamma minus 1 e to the power minus pi plus argument minus z t. So of course the important thing is what this the signature of this factor, this component, say. But I assume that argument of z is such that this is always delta. So this is somehow larger than delta. Some positive number. What? So positive number, yes. That is e to the power minus delta t. Dominated by this kind of factor. So you know by Lebesgue's dominant converses dominant theorem. One of the everybody of course mastered Lebesgue integral measure theory. So you know that this is convergent. So it doesn't matter. So alpha, beta, gamma, these factors, these are negligible in comparison with this exponential factor. Yeah, the t. Yeah, maybe. Yeah, okay. So in this way, this integrand is convergent, exponential decreasing, and we suffer no convergence problem, and also we got the freedom to deform the integration path in a derivative manner. That is, there is nothing horrible happens as imaginary part of S tends to infinity. So it is, you can consider as a kind of compactification. You can deliberately compactify this. I don't know whether, and at the infinity it's almost zero. It's really zero. And it's so meromorphic function on P1. And so this procedure is justified. Okay, so so far as this is true, it is this integral representation is valid. Now we want to analytically continue this integral with respect to z, not only this part, but of course we are in a kind of slit. Yeah, but that the analytically continue beyond the circle's boundary of convergence. In fact, we have seen that hypergeometric function, so every hypergeometric function that is element of two-dimensional C vector space that is nothing but a solution space. Solution to hypergeometric differential equation. That is this hypergeometric differential equation. So theta z is z times ddz. And so u z, then u z is oh, this was integration of 0, 1. 1 over z. 1 over z. In any case, it doesn't matter here. We sum C1, C2. Pardon me? Integration of this function y. Okay, I can recall this notation. Y Dirac function y is this function. This one. We discussed much during so first 2 sessions I consacrated much to the meaning of Riemann surface. How interpretation of this kind of integral in terms of period integrals, cycles, integration over cycles, homological cycles on a Riemann surface of this type, y to the power of m equals. In real, in real, it is complex number. So this does define a Riemann surface. In general, singular. So somehow mth root of this expression, that is rational function on the Riemann surface. So why this? Exactly this. That define the f alpha beta gamma z in terms of so chain integral. Yes, like this. So the point is that, of course, this integral satisfies this differential equation. That is, this differential equation is globally defined. So what I wanted to say is that this from this every f1, f2, every from this we see that every integral, period integral, say hypergeometric function, has singularities like this. Okay, singularities of there's a non-analytic or branching point, if you want, in z variable of every hypergeometric function R in the set of z times z minus 1 equals 0 and infinity. Z that is say so this is so I open this differential operator, then I get z square dz square minus z cube dz. The highest order term is this, of this. So it has singularity. So every solution has the singularities of this. The solution to this differential equation is contained in the z square 1 over z dz day, the highest order term, that where this highest order term vanishes. This is so that is say here. And if you make a change of variables, z equals 1 over w. Okay, I make a change of variables. Z equals 1 over w to see what happens at infinity. Z equals infinity, w equals 0. Then theta z will be theta w. That is a z dz becomes minus w dw. In fact, that is a remarkable fact that we use in toric geometry setting. So this becomes, okay, w I put it here, minus the theta w plus alpha minus theta w plus beta. That is say, I knew I get w square cube. Of course, you see immediately, and so w minus 1 goes 0 would be the signal losses. That is, w equals 0. It comes from here. So singularities of this hypergeometric functions are always 0, 1, infinity. In fact, I heard it was a bit stupid because I took out the H0 monodromy as generated by these matrices, yes, of course, yeah. So, in any case, it's maybe Sasha Dar did not follow this, and Denis also was follow, so maybe it's a kind of reminder what has been done during last 3 weeks or so. Okay, so and now so this function, yeah, in fact, analytically this can be analytically continued, analytically continued, 0 except 0 z equals 0, 1, infinity. That is, say, analytically continued to yes, 0, 1, z except so to continue analytically continue, so that that is, say, p1 minus 0, 1, infinity, 3 points. Yeah, at 0 it is holomorphic, so it is. But another one we had alpha plus 1 minus gamma, beta plus 1 minus gamma, 2 minus gamma, z, isn't it? That is z to the power 1 minus gamma. Like that. This is second solution. That is certainly has singularity at z equals 0. Z equals 0. Another hypergeometric function, so it says 0. It does have, so you have already seen that by an expression of H monodromy matrix H0. So that, and now the obstacles are only here to yeah, 3 points, yes. And the most important interesting information on this function, that is monodromy behavior, is somehow concentrated around these 3 points. So that is equivalent. Say that 0. I had 3 loops. So now let us consider what happens. Z tends to infinity. Z tends to infinity. Yeah, Z tends to infinity. Our next task will be to express. We have two these functions, hypergeometric functions. In terms of series, express. Okay, that is, say, it is. That is, say, examine the behavior of hypergeometric near infinity. Yeah. That is, say, express these hypergeometric functions in terms of series, convergence series, in now, instead of consider the variable z, consider 1 over z. That is, say, this must be something like this: a m 1 over z to the power m 1 over z to the power something lambda. This kind of thing. lambda. In fact, you can read off lambda from here. Lambda is alpha or beta. So very rough. So W is one of that is W that I introduced here. Yeah? W that I introduced here. So it is expansion in W. In W, some chart. C minus infinity. And chart. Yeah. And so you see that as you put W equals 0, this equation turns into the dominant part of some differential operator will be here. So W equals 0, W around W 0. So this part somehow you can consider a kind of perturbation. So this is the dominant part of the differential equation. To understand the dominant asymptotic behavior as W tends to 0, you can understand with read off from this expression. That is minus some function u w equals 0. That is u w is and if you consider this part, then you get higher order terms. That's the structure somehow. So that is analytic continuation of this Hypergeometric function defined in the neighborhood of 0, yeah, and then they're inside of unit circle, can be expressed by means of f okay, if I have f1 and f2, that's the same thing, but up to constant term equals some I have two hypergeometric functions, say let me like g1 what was that? Yes. So these are Gj W, say one was that, convergent in and so these capital G1, G2 looks very like this kind of series where they Gauss hypergeometric series. Yeah? It's a kind of simply you modify the parameters that present in the coefficients, and they get these these functions, yeah. So we can consider as component series that are also solutions to hypergeometric equation. The same equation. The same equation. Hypergeometric differential equation. So the solution space has C dimension, complex dimension 2, of course, and you can find these complex numbers. So our next task would be to find out these complex numbers, in fact, it depends on J. Yeah, it depends on J. I have 2. So I get 2 times 2 matrix, F1, F2 would be expressed in terms of C1 G1, T2. So this is the base change matrix. Base change from, say, z equals infinity, from z equals infinity to z equals 0. Yeah. And the inverse matrix would be z0 to z infinity, but it is not non-degenerate. We'll see it later. So this base change matrix is called connection matrix. This change matrix is called connection matrix. So connection between 2 types of two types of bases. So this is global problem, yeah. And so in the modern mathematics, this is one of the most difficult problems, that least studied problem. Least studied problem, huh? Yes, this kind of problem, yes. I mean that to connect what is happening in locally, z equals 0, and what is happening z equals infinity locally, but not to be satisfied with local description, but to understand the connection, the relation between them, to connect them, to get express concrete this matrix in terms of alpha, beta, gamma. That's all. That we have only everything depends on 3 rational or complex numbers, parameters, alpha, beta, gamma, and everything shall be expressed by means of these alpha, beta, gamma. In terms of gamma function, and here in this structure of this matrix, yeah, very intriguing, and yeah. So this is one of the. So, for example, in the literature, so wall crossing, you maybe you hear, listen to wall crossing. Yes, You may. So what is the wall here? Wall is that, in this case, simply z equals 1, and that's so that. So our situation is very, very simple. Yeah. So one-dimensional. And if z in several variable cases, it is this singular point, single loci may have. Huh? Yeah, yeah. Z equals 1. Yeah, that where this the series stop to allow analytic expansion. You cannot analytically expand. Yeah. Yeah, you can, but how to say? You cannot continue this series expansion in a simplistic manner. You shall do something, of course. There is a way to. There is a way to. So this is somehow to circumvent this this singular point and continue further. That's analytic continuation. Yeah. So this kind of story, yes, this is one of the. Yes, maybe you can hear such kind of problematics in different contexts, but the first most elementary case that you should study to further do research, examine this wall crossing procedure is here. And one solution I have already given in terms of H0, H1 infinity. But it is not so explicit. So you don't see how you cross the wall. And now making use of this expression. So where is it? Yeah. So wall crossing will be done in the following manner. In this very simple situation. So this has poles 0, 1 positive and minus alpha etc. So we have taken this integration path somehow and made this and deformed in this manner. And now the next week we should deform this integration path on the left hand side, on the left, like this. And this will give rise to summation of residues at these poles of this part. Yeah. So it will be a summation of really the alpha plus s equals minus m, positive integer, okay? You gather the residues. Then you see that here s will be s to the power minus z, s to the power s to the power minus alpha minus m, isn't it? And other coefficients, some coefficients, dependent on gamma functions. If I gather, if I calculate residue at these points. So this is exactly z to the power minus alpha was exactly this. Yeah, exactly this. Z alpha or beta. So next time we will. This is some very rough idea, and we pass to precise examination, calculation of all these coefficients. That is, say this, we calculate this connection matrix in a very concrete manner, and further we shall understand the geometric meaning, even yes, algebraic geometrical meaning, yes, that we want to relate it to Todd class. Okay, Hirzebruch, Riemann-Roch theorem, and so on. That is somehow very further aim, but yeah, at the beginning, yes, we shall study this mechanism, how to get this precise calculation, precise expression of connection matrix in terms of analytic continuation of integrals. Analytic continuations, this kind of integral, Baring-Barnes integral. Okay, so maybe today